Okay, so just for the record, this is Leipzig Gophers 19. Welcome everyone, and we will have a presentation on etcd. Michael, take it away.
Thank you, and thanks everyone for joining around the world. For some people it's early, for some people it's late. So that's great to see you all. So so I got a couple of slides just to set the scene before we go into like hands-on demos, and even like I can show code path if that's of interest. But before that, so the title says a journey into the Kubernetes ListerWatcher rabbit hole, and it doesn't say anything about etcd. So you're not in the wrong call. So there's a question in chat here. Hello, oh, from Colombia, crazy. Hey, Cesar. Martin, just a question. Can you take a look at the chat, please, if there's questions, so I don't have to always jump back and forth.
Yeah, I'll do that.
Thanks. So the reason why I actually got into like looking into the internals of etcd were I had a couple of questions while working on Kubernetes, and some of them just didn't make sense to me, how they work and how they are realized internally. And so I basically looked at from a Kubernetes client perspective through the whole chain, and ended up diving deep into etcd. And there's a lot of things that I learned and that actually helped me during my work. And so I proposed making a talk about this. I actually even wrote a blog post about etcd internals, and the feedback was great. I heard someone from Alibaba actually saying that they use this blog post to onboard their developers and learn about etcd and Kubernetes, because there's so many things that etcd provides and that are used by Kubernetes, maybe not all exposed, but at least used by Kubernetes. So it's good to know this as well, even if you're not really directly working with etcd, but maybe on a system like Kubernetes. And the Kubernetes ListerWatcher type or interface is an interesting one because it gives you some neat guarantees in the system to interact with Kubernetes. And you can even further abstract the ListerWatcher interface into something meaningful for your work, even if you don't use Kubernetes at all, because there's a pattern behind this that I'm also gonna explain, which is really useful. Okay. So how it all began, I started with a couple of questions. And if you're not really familiar with Kubernetes, and you see Kubernetes for the first time and you see all these components like distributed microservices and so on. And by the way, Kubernetes is written in Go. The first version was not written in Go, it was actually written in Java, but then like the whole open source train is in Go. And then you might wonder, how does this Kubernetes thing work? And if you peek into the system, you will realize that there's a lot of actors or processes, not actors in the sense of an actor framework, but more like a process or microservices. And there's no central coordinator. There's no central brain or orchestrator. It is more like a choreography amongst these different processes. And there's a couple of blog posts, like Joe Beda, one of the co-founders of Kubernetes, wrote one, and I wrote a couple of blog posts on Kubernetes as well. And I realized that a lot of things in Kubernetes are based off events and state changes in the system, which are propagated asynchronously from the system to your controllers. And so that got me actually deeper into the mechanics of Kubernetes, still not in etcd, but at least deeper into the Kubernetes internals. And then I saw from like thought leaders in the industry, like Darren he's working, I think now, he used to be at Rancher, and then Rancher got acquired, I think by SUSE, if I'm not mistaken. So he's a brilliant and smart guy, and he said that there's so many things and different terms thrown around in Kubernetes that you can easily get lost as an engineer or developer on top of the platform, like level and edge triggered and open world and assumptions, etc. And yeah, this kind of theme is also what I see with new developers onboarding in our team. When they look at Kubernetes, as so many things, like the learning curve seems to be pretty high. But if you really dig into the system or into the architecture of Kubernetes, it's actually built on very simple, and simple not in the terms of dumb, but simple as like robust and primitive approaches that then more complex systems are built on top of, like the whole framework. So And then based on all these questions, Tim Hockin, who also is like one of the leaders and leads behind Kubernetes, he wrote a couple of blog posts and gave many presentations on how Kubernetes works. So definitely check out these 3 slide decks he has on, I think it's Speaker Deck. You can just search for Tim Hockin and then his presentations, and you will find that. And they are very, very, very good in terms of the knowledge that he shares there. Okay, well, and then I came to a point, well, I kind of got so again, Kubernetes is, if you will, it's event-driven in the terms of that these controllers react to state or events coming from the system, and that they do something in a control loop manner. But the question is, what makes an event in Kubernetes? And then how do these controllers actually retrieve these events? And how do they like react to it, like reconciliation? What is that? What is the difference between edge and level trigger? What is actually this ListerWatcher interface, which all these controllers use under the covers to get the event stream? And then the next question was like, well, what if a controller is down and it actually misses events? Would that create corruption or like invalidate the business logic or so? Or is that actually okay to miss events for downtime or availability concerns? Then also when you start a controller or an operator in Kubernetes, operator is just something that like you program Kubernetes to do on a specific type, like you can write an operator for Postgres to manage Postgres databases in Kubernetes, for example, right? And when you start it up and it triggers this ListerWatcher interface, which is basically an interface composed of a list and a watch method, and it calls this watch, you always see add events, even though the system retrieves information that is already there. For example, the Postgres database might already be there, but you still get an add event. It's like, wait, it's still there. Why am I not getting a modified or an update event? Why is it always an add event that I get when I boot up? Next question is, how do I deal with eventual consistency? Like in an event-driven or asynchronous system, you have always these problems if you have multiple actors working on the same resource or trying to update the same resource. They could be like their view of the world could be well, stale or actually different. And then how do you prevent these issues that multiple actors fight over each other and incorrectly overwrite and or maybe corrupt data in the system? And then a critical component of Kubernetes, and like it's said to be like opaque and you shouldn't worry about this, but it's actually very important to deal with like optimistic concurrency control and eventual consistency of the system is called the resource version, and we'll cover this as well. But the question now is, if you see this in all Kubernetes objects, like if you retrieve a pod or a service or whatever in Kubernetes, you always see resource version. But if you look into etcd, where Kubernetes persists all this stuff, resource version is not there. It's not persisted in that object that you see there. And I'll show you that in the end. But if it's so critical, why is it not persisted? Like if you crash, like if Kubernetes crashes, comes back up, where does resource version come from? And last one, well, which role does etcd actually play in the whole Kubernetes architecture? Why didn't they use Zookeeper or roll their own or message bus or Fabric, right? All these questions that came up was like, okay, I get it. And then, well, I still have more questions now. And that's the rabbit hole, right? The whole thing that got me deep into the rabbit hole. And so I started writing a blog post series called the Anatomy of Kubernetes ListerWatch, which basically looks into behind this whole interface. And there's a lot of components involved there. From the left, it's basically these controllers, how you implement them and all the pieces that make a controller. In the middle, there's the Kubernetes API server, which like all these controllers talk to, and then the API server does validation and all this stuff. And then the API server itself is stateless, so it needs a persistence layer, and that is etcd. And initially, I tried starting like because it's a series, I was thinking, let's start with the client. For me as a user or developer, usually you don't worry about etcd, you worry about the client and how it's implemented. But then I realized that there's so many questions that I can't answer here because they depend basically on some guarantees, at least in the API server or in etcd. And so the blog post series actually starts with etcd at the core, basically. So brief overview on Kubernetes architecture before we then go into etcd. So in Kubernetes, we have, again, these different processes, which like there's no central orchestrator. They react to these changes and then talk to the API server. For example, the scheduler, controller manager for all these Kubernetes known objects. Obviously, we have etcd for persistency. Then we have the worker nodes where the applications and the containers are executed. And then we have things to talk to Kubernetes, which behind the scenes, it's all REST APIs. So the SDKs, the UI, kubectl, the CLI, they all use the REST API. They talk to the API server. So everything goes through, as the creators of Kubernetes said, through the front door. There's no component directly talking to the scheduler, for example. So everything goes through the API server. So the API server is more like a gatekeeper and doing validation and defaulting and transformation of objects to different versions, for example. And the API server is also the only one talking to the database. So there's no direct access from a worker or the scheduler into the database, everything through the API server, which also simplifies the architecture because the whole transformation, decoding, encoding is handled by API server. And everything is stateless and backed by this durability layer here. Any questions so far? Looks good, right? Okay, so let's talk about etcd. Here, I just say KV, like key value store, because that is the kind of backend that the API server uses in terms of etcd. But you can also bring your own database for Kubernetes, because Kubernetes abstracts the storage layer. And so K8s 3S from the Rancher folks, they use SQLite. I think Microsoft in their managed environment, they use Cosmos DB, if I'm not mistaken, at least maybe parts of it. So it's pluggable, but the majority of installations and Kubernetes deployments is on etcd. Okay, so there's a lot of stuff going on. This picture is basically just saying we're going to focus as part of this whole ListerWatcher journey. We are going to focus on etcd, but I will provide some pointers and hints as use cases for the patterns that we see in etcd, how they are used in Kubernetes. So hopefully you will, if you're not really too deep into etcd, you will maybe learn something about Kubernetes as well. So what is etcd? etcd is a distributed reliable key value store for the most critical data of a distributed system. That's a mouthful. So what in a nutshell, what does it provide me? First of all, it provides a simple interface, which either is through HTTP or gRPC, like there's a REST interface or a gRPC interface. And there's like, you get the put and the get verbs to like write something into etcd and retrieve something from etcd. The API is pretty minimal, which is nice. It is a key value based storage, meaning there's no relationships, like it's not a relational database. It is literally keys and values that you put in there. And the clients, they use strings, but under the covers, it's all bytes that are being used for keys and values. And then I think one of the features that etcd is most known for is watches. And we'll go deeper into watches later. But if you look for something like Zookeeper also has watches. I forgot if they actually called watches in Zookeeper. They actually might be called watches, but they, until recently, they didn't really provide the same features like in etcd, and this was fixed. Like you could have persistent watches. When a key changes, your watch keeps is still there and will give you more information. It's basically a push-based notification. But what you don't get in etcd is time travel capabilities that you can go back and say, stop the watch at this kind of node at the time t and not at now. So etcd gives you this capability to do time travel on a watch. And I'll also show this later. So etcd kind of revolutionized the whole state change notification in distributed systems. Obviously inspired by systems like Chubby from Google. It's written in Go. It's good. It's got a good solid library, Go package, and it was just the version 3.5 was just released, and there's a lot of stuff that you can read and learn about etcd. There's also a good paper or talk that describes the consensus engine behind etcd, because etcd provides strongly consistent reads and writes, also called linearizable or linearizability, meaning something that you write into the system will actually be reflected to all the other participants when they do the read. strictly speaking, there's more to linearizability, but in a nutshell, that's kind of the global view of a system. When you write something in, then the other ones will see the same, and you will also see the value being written at point in time. And that is something that's a nice property to program against, because you don't have to really think hard about other consistency or anomalies in the system. And it also works in a scale out fashion where you can have multiple etcd instances running in a quorum of 3, 5, or 7 or 9 nodes. And behind the scenes, that is all handled by Raft, the Raft consensus protocol. And there's a nice thesis by Diego Ongarao, I think is his name. And he created Raft as a means to simplify consensus in distributed systems, which usually was using Paxos or different variants of Paxos. And so that is etcd uses Raft and kind of popularized Raft too. But I'm not going to cover Raft and consensus in this presentation today, because there's a lot of good talks out there which cover this area. Okay, so why did I cross this out here? The web page still says that you can store data in hierarchically organized directories. That was true as of etcd version 2, and there's still blog posts out there which use this kind of description. But in etcd, you will basically see this. There's no hierarchy, so we don't have a folder or directory structure in etcd when we create keys. It's literally just strings. And if you create your strings in a way that they look like folders, like /folder /1 / something, that's fine. You can basically mimic a hierarchy. But under the covers, it's literally just a long string. It's just a byte array that gets written into the database. Okay, and yeah, watches are pretty important and significant and heavily used by Kubernetes as well for efficiency reasons. Instead of polling the system, hey, what has changed? The watch will give you all the changes almost like in real time, very fast over the wire, and also in a consistent manner that you will see changes to an object at T1 and later changes at T2 and T3, you will see them in order through the watch. And so that gives you a nice property that you basically progress over time through the system. Okay, so that was enough on that I had on the slides. Any questions so far or corrections?
So if they say it's not on the web page, if they say it's hierarchical, they mean like you can mimic hierarchy, because like otherwise it would be like a kind of wrong description or like outdated description.
Might still be outdated, yeah,
okay.
Because yeah, I think it's outdated because it puts too much emphasis on the hierarchical. And it was hierarchical in V2, and people were actually using the client of like ls and then going into directories and picking directories. That is not possible. And people were like, oh, where's my ls command in etcd version 3? And it's like, yeah, we don't have these hierarchies anymore. Let's use prefixes. Okay. And I'll explain this in a bit. So I have prepared a couple of notes here, and I have created a gist, so I can share these notes later. But this is just me, like my little helper to not forget any of the important steps that I want to cover. So what I'll do is I will run etcd with Docker on my local machine. And I'm using the Bitnami etcd packages. They provide clustered packages and all the stuff. I'm just running one node here because for the purpose of explanations, that's totally fine. But the Bitnami packages are pretty neat. And then once this is running, we can access. Oh, by the way, I think this is better now. Size?
Yeah, that's better for me. It's
okay,
better.
sorry. Yeah. So now I'm into the etcd container. And it's, I think it's Ubuntu or Debian. It's a Debian system. Okay. And the next step is I'm going to define an alias. So there is a command line tool, etcd-ctl. That's how you can imperatively interact with etcd and query the members and endpoint status, which basically tells us what are the different endpoints available, or member list, I think, is another one, which we have currently one member. We can also do JSON output. We can use JQ, which makes it a little bit better. So we have one member as an ID, no peers, it's just itself. And you also see here ref term, and kind of headers. Headers are important in these responses that you get back from etcd. They tell you a lot and useful information about the system. And currently we are on ref term 2, meaning whenever there's a leader action in etcd, the term gets bumped up like an epoch number counter, so you can fence off other nodes. But again, we won't cover consensus too much. And now I need to update my JQ CLI, because I'm going to show some base 64 decoding that you can do with JQ, but the version that is shipped with this container is outdated. So just...
Hey, Michael, okay. the storage...
Oh! Hey, Bill!
Hey, man. No, I was going to miss this. The storage for this database is just given to you for free. Like, you don't even have to worry about.
Good point. I completely missed this. It's almost like we have a script and you keep remembering of what I need to cover. So actually, this is also a very interesting piece that I cover in the blog post. So the blog post is on my web page, and it's called Onwards to the Core. I go more into the actual storage layer of etcd, because Bill is right. etcd is more than just like a consensus engine. At the heart of etcd, in every node, there is a database layer, which is bbold. And bbold is written by Ben Johnson, I think. And etcd...
Yeah, Johnson.
Yes.
Yeah.
Yes, Ben Johnson, yeah. And he archived the project because, like he said, the API is stable. There's not much to fix there. But because etcd kind of started pushing the limits of BoldDB, and they had some specific requirements, they forked it, and since then kind of maintain the fork of BoldDB. What is also nice with bbold or BoldDB, I always confuse them, bbold, BoldDB. There's Bold is actually inspired by the LMDB project. If you know OpenLDAP used to have Berkeley DB, BDB as a backend, but I think it was in 2010 or so where they realized for scalability concerns and some other properties that Berkeley DB didn't have, and also space consumption, etc., they had to rewrite the storage engine. And Howard Chu was leading that project, and he's also brilliant, I think, kernel storage file system developer in the Linux space. So he wrote LMDB, or he led it. And LMDB is using B plus trees, or yeah, I think it's called B plus trees internally, to do the whole storage management. So if you really want to go deep and into the nuts and bolts of etcd, you should take a look at BoldDB, also at LMDB. I have all the links here in my blog post that cover more of the BoldDB specifics. But BoldDB has one nice property. It had many properties, but one nice property is that it allows you to implement multi-version concurrency control, meaning multiple readers can get different historical views of the database, whereas only one writer is always allowed. It's almost like a read-write mutex that you have, like you let multiple readers read from the system at different points in time. You get like a snapshot view, and then writer or a writer is only appending or writing this into the system. And MVCC is kind of used, or multi-version concurrency control is also used in etcd, but at a different layer and different implementation. But BoldDB actually also gives you these kind of properties to do snapshots and kind of time travel queries as well. Did that answer your question, Paul?
Yeah, that's cool.
Cool. All right, so I have JQ, and let me show you. So E is etcd CTL. Let me bump this up a little bit here. Let me do a get. And I could specify anything here, but the convention in etcd is like to mimic hierarchies to start with a slash. Now, if I say, let me just do this for now. I don't get anything in response. If I use JSON output, I at least get a little bit more output, and I only get a header back. But the header already tells us something very interesting. It tells us there's a revision. And the revision is 1 here. And for every etcd instance, that means every member that joins a cluster, it always starts at revision 1 if it's empty, unless there's already data which it kind of recovers on start. And revision is important because etcd is based on the concept of a log, not log like CK, but log, L-O-G. And if you're familiar with Kafka or these kind of systems, it's basically an append-only model that they use. So changes that you make into the system, even on existing keys, like when you update a key, they will never overwrite existing data. They will only ever be appended, which is nice because you can ask the system, hey, what did that object or key look like at T3, like timestamp, whatever, right? The downside of this is if you only ever append, you might run out of disk space eventually, right? Otherwise, we would all have these kind of log structured databases. And so there's a concept of a compaction and a defragmentation as part of etcd. And I'll cover compaction in a bit, what it means here. But revision, whenever there's a change in the store, meaning whenever you put something into the system, even if you're just overwriting the same key, revision gets incremented. It's a monotonically increasing counter. And that, if you get nothing out of this presentation, remember the revision, oops, as a monotonic counter, because a lot of things will get clear, even in Kubernetes land, if you understand that revision only ever goes up. And this is a very nice property in the system. And again, if you know Kafka, think of it like an offset, where the offset starts at 1, and then you write into the system, and it just ever appends, and you have a cursor where you can jump through these offsets. Okay, so there's nothing in the system. Let's do this, for example. We only get back our header, right? But no keys, nothing is in there. And we know that there are no keys because otherwise etcd would tell us, like there would be another property here being in the JSON response, which would tell us the keys, the number of keys. There's a counter in there. So currently the system is empty. It always starts at revision 1. That's how we know that the system is fresh, it's clean. There's at least nothing in the key database. If you really dig into the bold DB layer, which we do later, you will see there are other buckets. So bold DB is organized in buckets for cluster membership and like cleanups and other stuff. So there is actually something in the bold database, but from our keys, and this is what users interact with etcd, nothing is in there. Okay, let's put something in there. Let's create some data. So this only like primitive for loop, put keys. And you could say I'm creating a hierarchy here, folder keys, and then the number 1, and the value is just 1 here, which simplifies some of the stuff that I'm going to explain you in a bit. But again, there is no hierarchy. I don't have to create keys first and then put something in under keys. It's literally just a plain string that I put in here. Okay. System accepted, acknowledged. And now if we look at the data, let's take a look at this command here. It's basically saying, give me everything that starts with a slash. Prefix is basically saying it's almost like a crab. Think of it like a crab. Everything that has or starts with that slash, please return it to me. If I don't do this, if I don't specify it, nothing will be returned because by default get will do an exact match. It will do byte comparison and it won't find any key that has a slash because there is no key that is just a slash. I have not created this, right? But if I do a prefix, which is basically telling etcd everything that starts with like a range, and we'll cover this in the RPC section later. It's a range, everything that starts with a slash, please give it to me. And voila, we have some data. Let me show this here. So what do we have here? So we have our header. Revision is now 6. Remember, we started at 1. We created 5 keys. That's why now we are at 6. And let's look at the keys. First of all, the keys are base64 encoded here. They're not base64 encoded in the underlying system. I actually don't know why they are represented base64 here in the client. But there's a nice command. That's why I had to upgrade my JQ version. JQ allows you to decode these values. So let me do that. So clear the screen. Okay, so now we see that the key here is key/1, the value is value 1 that we did in there. So now there's a couple of things which I initially didn't understand from the documentation in etcd, because they were talking about crate revision, mod revision, version. There was even generation is in there. And I was like, what are all these terms and concepts? So let me clarify them for you. Crate revision is when you create the key, so the key doesn't exist. Crate revision will tell you or will be set at this current revision. And so since we started at 1, the first key we created was this one. The crate revision is actually 2. Now, because it was a key that didn't exist, the modification of this key is also set to the same revision, 2 in this case. You will see later when I do modification of this key, mod will go up, crate will always stay. And that is how you know and can see at which point in time was this key changed or created. Right now we know that at revision 2, this key was created. And 2 and 2 here means it was never modified since then. And this will also be told by version. Version will also be bumped up if you do modifications on a key. So that's a more simpler way to see if there have been modifications. Hey, Calicia, hello. What a party, nice. And then if you look at the other keys, key 2, 3, 4, you will see the same, crate revision 3, crate revision 4, right? So for every key and every operation that you do, we'll not talk transaction for now, but if you do a put into the system, the revision will be bumped up. So each change in the system gets its own revision. And the last one obviously is 5, and so we have 6 and 6 here. Okay, you also get back a counter, like how many keys have been returned. And that's how you know whether the object was found or not. If you don't get a counter back or it's 0, then you know there's the key that the get didn't match. Any questions so far? Good. So next one, let's update the key 1. So I put the value A1 into this key, and I'm saying, please give me a JSON response. The reason why I'm doing this is very useful. If you do a change modification into the system, you actually get back the current revision as of now. So meaning right now, revision is 7. The only problem there is that could be like multiple actors now also doing changes. So the revision actually might progress already by the time I get back this response. So you shouldn't really rely on this number that this is there's no God's eye view on the system. But there's one property, which is if you start or watch the system at this point in time 7, and then the system will basically give you all the changes then afterwards. So you have at least a linear history or timeline that you can travel from there. So you're not going to miss changes into the system, at least not under normal circumstances. Okay, let's get the key, the updated one that we just did. And so this is key 1. I forgot to do the decoding here. So this is still key 1. You see that the value has been updated to A1. The revision is 7. You also see this, the current store revision is 7, so there were no modifications since then. Otherwise, this number would be higher. The mod revision is now 7. The version got bumped to 2 because it's actually the first modification of this key, but the crate revision stays at 2, which is nice because now we could go and ask, what did this key look like at revision 2 or any previous revision? Okay, that is the time travel aspect that I meant. Okay, let's delete this key. We delete the key 1. Revision gets bumped up. Again, every modification to the store, and the deletion is a modification, bumps the revision counter. So think of it like you get multiple put and delete requests, and there's one writer that serializes all these requests and then always bumps up the revision counter if the write was successful. Okay, so the key is deleted. Let's check if it actually is gone. So we can again say, get me all the keys starting with the / prefix here, but only get me the keys. I'm not interested in the values. And you see the keys gone, right? We only have 2, 3, 4, 5. And now let's take a look at the key at revision 8, which is our current revision. We don't get back anything because the key is gone at revision 8, right? We deleted it. So why am I showing this? Well, under the covers, the key is still there. As I said, nothing is ever erased from the system. In etcd, what they do on a key that is deleted, they put a tombstone on it. Same with like in Kafka. So basically they delete the value, but the key is still there. You just don't see it when you do this retrieval, the data retrieval. The key is gone from the object model, from the index, but in the database, it's still there. But what we can do now is, since we know the current store revision is 8, we could go slowly back in time. Maybe because we know that there has been a key 1, but maybe we don't know, and we just want to query the system backwards and ask whether there was a previous version of this key. So what we do here is, again, we try to get the key, but now we specify revision 6, almost like timestamp 6, right? And there we get back our key with value 1. I can also show you how this looks like for 7, where we did the modification. So at 7, right, the value, we did this modification on A1. At 6, well, we didn't do a modification, but what etcd does behind the scenes, it will basically walk backwards in time to find a revision that is not higher than the specified one for this key. And because there is 1, 2, it will give us that version of the key at that point in time. So there's no way to ask etcd, hey, please give me all the revisions for that key. You would literally have to walk backwards in the system to do that. And by walking backwards, what I mean is you query the system, like here on 7, you see mod revision is 7. So you do 7 minus 1 is a 6. And you go backwards, you see 6. And if you do want to do it again, let's say we want to query it at 2, we see it initially. Let's go back one more to 1. There's an error from JQ because what I'm passing in there, there's no content. Like it didn't exist, right? And that's how you actually can slowly walk backwards in time to figure out the different versions of a key. But there is no direct API in etcd. Okay, any questions so far?
Just a short question, like, is it something that you run into, like you want to see like all the versions of a key, and are there other tools that do that, like manually, like that you don't have to type this manually, or is it something that doesn't come up actually that much?
Well, that's actually more a question, it's a good one, because it's a question on system design. Is your logic required to see all the changes? And that's what we usually refer to as edge-driven or edge-triggered, right? You can't miss any change in order for your logic to be correct. So for example, think of a counter or like an add operation, add 2, add 4, add 6, right? If you miss 4, the result will be wrong, right? But if I give you a state like sum is 5, sum is 9, that's basically a level. Your logic can use the level as the source of truth. And that's what Kubernetes does. So if you look at Kubernetes, it's very much level triggered, where you get a full like representation, the state of the object. And even if you miss incremental changes, for example, on a container or on a pod there, your logic would still work because it's not relying on every change, not on every edge. This is from control theory, right? Like systems design. You literally just get a level. And if the level in between has changed, it doesn't really matter because you just try to reconcile on that current level that you see from the system. It's a little bit different thinking. And that's why we don't see this being, at least I haven't seen it, that's a requirement. And there's also something that gets in your way, which is compaction. And that's what I want to show next.
Yeah, I just was like thinking about like debugging or something. Yep. But thanks for the answer.
Yep.
There's no way to know they're not auditing who's making these changes, right? They don't care who did it. They just care about the change.
There's tracing and certain auditing events in etcd. So etcd, the API, the gRPC API has auditing and logging in different places and at different levels. In fact, they also just switched to using the Uber SAP logger for like easily doing debug or stack tracing and all the stuff in version 3.5. So you will actually see modifications. I don't know if they persist all the key-based modifications because there's just a lot of data and volume that goes in there. Because etcd is also often used for leases and locks to implement distributed locks in the system. That means you create a key and you basically become the owner of the key. And so other actors in the system try to fight to become the key owner. It's almost like a distributed lock, right? And that is based on leases, the concept of leases in etcd. And leases also do modify the store. So there's a lot of put operations. So the revision basically in a live system will be very high because of all these changes. And even if you would persist all these changes, as Martin was just asking, you would eventually run out of space. And that's why you need to compact the system. Okay, so we deleted that key. So I'm punching on this key one here, but because it's very simple to show the system behavior here. So we deleted it previously. Now let's create it again. So the revision gets bumped up to 9. Let's query this key again. Let's do just the get here. Get key revision. We don't need to specify a revision. If you don't specify a revision, it's basically now, as of like now. And so we see that the key is there. It has a create revision of 9 and has a mod revision. So etcd won't tell you that this key previously existed. This is almost like forgotten. And the reason for that is that the internal index structure that etcd uses, and we'll come to this in a bit, has a concept of generation. And whenever a key is deleted, that generation, which holds all these different create and mod revisions that you see here, it is sealed and a new generation is created. I cover generations in detail in the blog post, but essentially what this means, it's almost like a generation is sealed and kind of immutable at that point in time. And if you recreate the key, a new generation is created, and there's no direct way to access the previous generation unless you know it. Like I could now go back and say mod like revision 7, and then you could go back in time, but there's no guarantee to get it because generations are used for compaction, to clean up the disk space in the system. We know that if a key has 2 or more generations, we know it must have been deleted previously, because otherwise there would just be 1 generation in the index. And that's how etcd efficiently does compaction. It just looks at all these keys at a specific point in time, and it finds all the generations which are sealed or closed and have a revision lower than this one. So let me show you this in action. Oh, before that, let me actually show you the database, the underlying Bolt database. So so on the left side here is my local machine outside of the Docker container. And I can just copy over from the etcd server the database, which is in member snapdb. And I just copy it over. And then I can there's a nice little tool called etcd dump db, which is in the etcd repo, etcd.io, and then it's tools etcd dump db. It's a Go binary, just build it. And then you can say iterate bucket. As I said, the database has multiple buckets, and the bucket for the keys is key. It's called key. And then I'm saying decode because by default, it's going to be, I think, binary or hex encoded. So now this is the raw view of the database right now before compaction. And there's another interesting thing here. First of all, our keys are all there, right? Key 1 is here. It's created at 2, modified at 2. Then we did another one, an update here, key 1. We wrote the value 1. Obviously, it's created at 2, but we modified it at 7. The version got bumped up. Then we deleted it. Key 1 here, value empty. It's a tombstone. Well, there's a marker in here, which we don't see, but there's a tombstone marker in here, an empty value. And then created and modified and version get reset as part of a new generation. That's why we don't see this. And so we know this is the deleted key. And then we recreated it at timestamp 9 or revision 9 and wrote that value in. Now that means knowing these revisions, we can now go back and kind of resurrect the key that was deleted because it's still in the database. I haven't done any compaction yet on the database. And compaction can be run in etcd periodically. I think by default, it's every hour. Kubernetes runs it every 5 minutes, I think, because there's just too many modifications in the system. And you can also manually run it. I'll show that in a bit. But the other thing that I wanted to show you here is that the etcd dump db output structure is, this is the key, and that is the value. Well, actually here, that's the value of the key. Now this is a little bit confusing. So why is the key not keys 1? Why is it a revision 9020? So again, BoltDB is a key value database. The key in BoltDB is a revision from etcd. Like if you use BoltDB for other purposes, obviously whatever you do with the key is your choice. But etcd decided to not use the user-defined key that we use as the key in BoltDB, but the revision. Now this is interesting because that is actually the implementation of this log structure under the covers. By using the revision, which is a monotonically increasing counter, under the covers, you only ever append to the database. Every key is just going to be like increased, the number 2, 3, 4, 5, 6, 7, 8, 9. So it just grows forward in time. We never overwrite a key. And that is the way etcd models the multi-version concurrency control on top of the BoltDB under the covers. The value of the key is the key that you provide, here keys 1, and the value that you provide. And that can be confusing if you look at the database, because you would expect your key to be here and not to be something like a revision. In the blog post, it's like explained much more deeper and how the whole traversal works from etcd to database. Because the problem now that you have is if you want to look up this key in the database, or if etcd needs to look it up, it can't go to BoltDB and say, hey, give me keys 1. Well, because BoltDB doesn't have an index. It only knows about 2, 3, 4, 5, 6, 7, 8. That's why etcd internally has a B-tree index where they map these keys to generations which have created modified timestamps. And then based on these generations, they construct the byte key for BoltDB. Meaning if you are looking for that key 1 at created 2, you go to BoltDB and you give it 2 as the key, and then Bolt will give you back this byte array, which is key and value. And then you just need to unmarshal it. It's basically a binary blob, a byte blob in the system, and you read it out. You know how your structure is, like it's a struct in protocol buffer definition in Go, and then you unmarshal the value into a key and the value, and then you get your value back. There's a lot of indirection in there, but that is basically how this multi-version concurrency control is implemented from etcd on top of BoltDB. It's not using the keys that you provide, because otherwise you would overwrite data, which we don't want. We want to keep the data, right? We only want to go forward in time and never overwrite. But again, the problem with overwriting is, and not overwriting is, and only appending data is, eventually you might run out of this space, because BoltDB, right, would just hit the storage capacity. So there's a command to force compaction to tell etcd, please discard all values and information that you have in your index on points or revisions smaller than this number that you specify. And I think right now, the current store revision is 9. So all the revisions done in the system, all the changes have led to revision 9. That's the current revision of the whole store of the whole etcd. So I'm going to say etcd compact your whole store and discard all information prior to revision 9. Now, will that also delete other keys, like these keys? Will they also be gone? Let's see. Okay, compaction work. Let's copy the database over. And let's iterate again. So this is after compaction. We see that our key revision 2 is gone. So this guy is gone. We have 3, 4, 5, 6, which means the keys which were not deleted are still there, because otherwise it would be pretty useless database, right? If you throw away all the data, even if it still existed. So etcd will only compact and delete or discard the data or mark it as free in bold if it has a tombstone marker. And our key here, key 1, had a tombstone marker at 8, at revision 8 here, at this point in time. So it went ahead, because I set 9, it basically went ahead and found all the revisions of that key prior to a tombstone, or prior or equal to the tombstone marker. And so 8, it was deleted. Obviously, that can be deleted from the database. We don't need the tombstone marker anymore. And then it went back and it also deleted 2, because that has because we told it to forget everything that has been deleted before revision 9. But it kept our key, because obviously that key now exists, but it exists as a new generation. So the old generation is kind of forgotten. It's almost if you forgot your grandma because you didn't like her also, which you shouldn't. You should love your grandma. But imagine you forget someone else. That's basically the concept of compaction. You ignore them forever in your life. You never want to see or hear them, and then you compact your brain, and it's almost like you never met this person ever before. That is compaction. Any questions so far?
So only the ones that are being marked for deletion get compacted. So is Kubernetes performing that a lot more than just plain updates?
Yes.
Right.
Well, I think in Kubernetes, most of the time you on normal objects like pods and services and whatever, there's probably more updates than deletions. Depends on the controller that you write. Maybe you write a controller which does a lot of jobs which come and go and you delete them. But I would say generally there's more updates to an object or create update than delete. Now, Kubernetes uses leases and locks, or well, leases a lot in etcd. And these leases expire over time. So compaction also gets rid of all these dangling leases, which you don't need anymore because there was a new lease created from another, for example, leader or actor in the system. So I would say normal objects that you interact with are probably not often deleted and thus not compacted a lot. But these kind of leases and back-end system things that Kubernetes does under covers for distributed systems, availability and whatever, coordination, they also consume resources in the database. And I will show you a lifetime of a Kubernetes database in a bit, and you will see many, many leases and not so many changes on actual objects.
But I imagine even on a very large system, this database is fairly small, like megs, right? I mean, this doesn't ever get to gigs or terabytes of data, does it?
Good question. So the general recommendation is, first of all, back it with SSDs, because even though it looks like there's sequential writes here, the way etcd needs to look up and index your key to the actual underlying data structure is not sequential, meaning there could be a lot of random access. So SSDs, first of all, should be given in an etcd platform or machine. The next one is Bolt2B uses memory mapping. So the assumption is, meaning operating system mmap, the assumption is that the whole database can fit into memory for like this whole B3, B plus tree lookup and all the stuff and memory management. Now, the question is, how big can this database get? Well, in, I would say, enterprise Kubernetes environments where you have like multi-node, multi-cluster, there's probably a couple of gigs that come together, because it's not just pods and services or deployments. There's also a lot of events that controllers write into the system. And when I say events, I don't mean these change events. I actually mean events like user, like audit logs, for example, or my operator created another system event. So Kubernetes has different terms for events, but these kind of events also get persisted as objects in etcd. Now they take up a lot of space, and that's why Kubernetes allows you to split the etcd instances, the key space, and say everything that is like normal Kubernetes pods deployment goes into that etcd instance, and everything that is events which I can lose because they are more like audit related or like debugging related, they go into that etcd instance, because there could be contention, IO issues, obviously data volume size issues. So again, the recommendation is a couple of gigs, like 4 to 8 gigs usually is sufficient for large scale deployments. And that also means, because it's all mapped, memory mapped, the machine should have sufficient memory to fit the whole database into memory.
Plus, this is per cluster.
Well, per etcd instance. Like if you have a cluster with 3 Kubernetes master or control plane nodes, then you would have 3 etcd instances, and these 3 instances would have like 4 to 8 gigs of RAM. Each.
And the B tree would be like the in-memory index of etcd that maps its own key space to Bolt2B is kind of also in memory, if I'm kind of...
No, this is physical. This is on the, like, this is written in the blobs, okay. But because bold DB or bbold uses memory mapping from the operating system, from the kernel does the memory mapping, right? It's an mmap call. That is basically meant that the whole physical database is loaded up into memory. And what you want is to fit the whole thing into memory so that the kernel can optimize memory access. So you don't always have to punch the disk. Obviously for writes, you have to, right? They go, and eventually they will hit the disk, sorry. But for reads, it's good to fit that in memory.
Yeah, just because we are at it, like at these limits, like what is like the number of like compacted things, like compacted keys that would kind of fit into like 4 to 8 gigs, or like
it's a lot.
It's like
it's a lot. Like it's huge, like hundreds of nodes, Kubernetes nodes, I would say. And that by that I mean if you have hundreds of nodes, depending on how beefy they are, there's like thousands of pods running and churning the system.
Yeah. Yeah. Okay. Yeah. Fair enough. Cool.
Yeah. Cool. So that was compaction, the way things get compacted. Let's talk watches because they are interesting. So we inspected the whole thing. Watch a key. Okay, let's put a watch on a key. Well, let me actually go in here. Alias etcd is this one. And I just need to export my path because of JQ. Okay. Okay, so now I'm going to watch key 1, and watch is basically this persistent connection to etcd, which tells etcd, hey, I want to get notified when something changes on a key. And if you don't specify a revision on a watch, it's basically from the next change on in the system. So you don't get the actual value, but you will get the next change. And if there's no change, you won't get data ever off the system. But obviously we want to do something. So let me put something in there. Let's say our key now gets a value 1C. Okay, so we get obviously the change now. Revision is 10. This is important because as part of the watch, you now also get the revision back of the store. And if you start tracking the revision in your logic, in your application, or in your Kubernetes controller somehow, and you persist it somewhere, then if you crash and come back up, you can literally start watching from revision 10 next, like 11. Unless you haven't finished your work before, right? It depends on how you do snapshotting and checkpointing. But if, let's say, you perform a change in your system and then you checkpoint and say, oh, I got everything up to revision 10, and then you crash and you come back up, then it's clear that you have completed your work up to 10. And then your controller can start watching from 11 for all these changes on the key. And that's how you can make sure, again, depending on the downtime of the system, if compaction gets in your way, you basically lose events. We'll cover this in a bit. But let's say there's no compaction, right? That basically now guarantees you that you won't ever miss a change on a key. Because if you say, I got everything up to 10, I did my work, and then I crashed, and I came back up, I completely forgot what I did. But the last one that I actually seem to have done is 10, like revision 10. So now I'm just going to watch on 11. And so you can specify during your watch, you can give it a revision. If you don't give it a revision, it's basically now, which could mean 20, 400, 5,000, whatever the revision is. But if you want to have like a linear, gapless view of the changes, then you can give it a revision. Okay, so as part of a watch, you get an array of events here. This one. If I would have put a prefix in there, so watches can also be on prefixes or ranges, right? You would get multiple events. For example, key 2 might have also been modified or so at that, like during that point in time or later. But in this case, I just got this one event here on this modification. And then we have the typical create mod revision that we know about. Okay, so let's do another one. Same key. Okay, so the watch just keeps appending, right? Here, this is the old one. And then here we have the new one, and so on and so on. And you will always get the revision of the store. Again, now you can checkpoint, you do your work, you checkpoint, and you crash, you come back up. If you know Kafka, it's basically the same principle behind that. which is a very nice property because you don't have to pull and like do gets against etcd all the time, which the Kubernetes creators wanted to avoid, that you have the whole fleet of nodes asking the API server and etcd, hey, did something change? No. They basically inverse the model, which you should do if you have like a small control plane fleet and a huge data plane fleet. You inverse the model. Instead of having them to ask you, you push out these notifications, these changes for scalability and availability reasons. Right? You just tell them what the changes are. That's a watch. And behind the scenes, it's using gRPC streams, bidirectional streams. So one stream is used from the client to etcd to initiate watches and control messages, and the other side from the server to the client gives you the changes through the channel. So that's done on with etcd. Let me delete it again, this key. So let's see it, because there's something that I want to show you. So now we see a type in the event here. Why didn't we see the type here on the update? We see a type 1 here. If you look at the protocol buffer definitions for these events in etcd, 0 is put, 1 is delete. 0 here as part of my JSON output is ignored. It's a default value, so that's why we don't see it. But 0 basically means it's a put, a change, and 1 here means it's a delete. And those question markers here, this is just garbage from the base64 decoding because there is no value in there. This is an empty value, as we saw on the database before, right? And there's also no crate revision, right? We only see this mod revision to 12 here, which means this key has been deleted, which is also what this event tells us. Type 1 means deletion. So we now understand what is a crate. If it's a crate event, you don't see crate, you will see put. But you will see crate and mod revision being 9 in this case, would be 9. So you know that key has been created. If it's 9 and 11, you know it has been modified. Still a put event, but modified. And then if it's a delete event, it's a distinct event which is called deleted, and then you know that the key has been deleted. And so based on this, you can now write your logic. Key has been created, updated, deleted. Create, update, delete. And this is what Kubernetes initially did in the controller logic. They had triggers for add, update, delete. And then they switched to fully level triggered logic, which is you don't even see these state changes anymore. You don't see, oh, that's an add, oh, that the pod has been updated, oh, that pod has been deleted. You will only ever get full representations of a pod, for example. And if it's deleted, it has a deletion timestamp. If it's not deleted, it doesn't have a deletion timestamp. And you won't see all the changes. You will only get the full object, meaning, hey, 3 instances of this deployment, and then you act accordingly. Whether before that you were down and you missed 2, 5, and then 3, doesn't matter. You only ever work on the latest state that you will get from the system. And this is this level triggered logic versus, oh, it was 2, and I need to do 2. Oh, it was 5, now I need to do 5. Oh, now it's 3, I need to go back to 3. You literally can miss event, and that is anticipated in the system. And that's how we build very robust systems as well as in Kubernetes.
Just a quick question. So it was implemented in this add, modify, delete style, and then kind of problems appeared, and or like it was kind of not ideal, and so it was kind of rewritten to include the full representation of what should be.
Almost, yeah. So the problem was that whole add, update, delete, or on add, on update, on delete callbacks. That led developers to write kind of spaghetti code logic, and then now it's an add event. And you also have to be careful of like in order delivery of these events, because otherwise if you do concurrency in your logic and you handle the delete before the add in your logic, well, it gets messy, right? You do the delete instead of the other way around. And so if you peek under the covers, and in the slides, I have shown this like these 3 boxes, right? If you peek under the covers, they still have the handlers on add, update, delete. But right now what they do is they do all the same thing, which is filling a cache with just the object representation. And then the logic of the controllers that you write, basically the interface that you need to implement in Kubernetes as a controller author, is not on add, on update, delete. You only implement a reconcile method. So if you write a controller in Kubernetes, you don't do on add, update, delete, you only do reconcile. And what reconcile does, it gets you a key, which is the namespace name of that object. You go into your cache, which has been fed by these event changes. If you try to look it up and it's not there, well, it's probably gone, deleted, right? And you might have missed it. if it's there, you take it, you take the representation. It might have already been changed on the remote system because you're in a distributed system, you don't know, right? And then you do your work. Now, the question is, well, what if I'm behind? Like, what if my cache is stale or behind the actual object, right, in Kubernetes? And you do some change and it's like, oh, that actually overrides that's something that Martin has done on this object, which is more recent. That is where the revision comes in, because Kubernetes uses this revision. They just call it resource version. Well, I'll show that in a bit. So revision in Kubernetes is called resource version, and they use this as a fencing token. So if I'm going to say to Kubernetes API server, hey, update that object, and I give it a revision, and API server sees that this revision is older than the current revision of the object, it's going to fence me off and say, please refetch the object. So, and that's called optimistic concurrency control that we have also in databases, right? That's pessimistic, that's optimistic. That's what Kubernetes does. Okay, speaking of which, we still have like 14 minutes left. I think that's good enough to cover Kubernetes. Any questions so far? Or more questions? I don't know, in the chat, anything, Martin?
All fine, all fine, all fine.
Okay, nice, cool. So let me stop the watch here. I don't think we need that anymore. So I have a kind cluster. Kind is a Kubernetes and Docker, which basically gives me a Kubernetes cluster or installation on my local Docker machine. And I can also do Kubernetes. K is kubectl. It's an alias for kubectl. Give me all the pods and all the namespaces. And there's not much going on in my system right now because I just installed kind for this purpose. We don't need much in there. But what I wanted to show you is the representation of an object of Kubernetes from the API server view versus how it looks in etcd under the covers. And there's a couple of things which are interesting. So let me get okay, good. What is it? Local path storage. This is a pod here that provides me storage volumes in kind. That's pretty neat. If you need to do volumes, volume management in Kubernetes, get pod this guy. Okay, that is running. Now I'm going to get the YAML representation of this object from Kubernetes. So there's a lot of YAML in here, blah, 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 blah. Let's just pipe this into a pod and call it API or pod K8s. This is the representation of this one. And let's copy the K8s database. So now I'm going to copy from the kind control plane the etcd database. Okay. And let's take a look at the database first. So we can do iterate bucket again, but now it's the Kubernetes database. And you can tell there's a lot of things, even in the cluster, which I haven't done a lot, right? And this is not really readable. So let's pipe this into code. Okay, can you see my screen? Okay.
Yeah, it's a bit small, but
I can increase this. Okay, so we see our friends again, revision. So this is the bold DB key, right? And here are the values. Let's take a look at the key first. We know our current revision of this Kubernetes cluster at etcd is 13,000 for like 443. The meaning that many changes have been in the system, and there's literally nothing going on into the system. I haven't like installed anything. It's literally just leases and endpoint updates. And Bill, that's what I meant. There's so many things going on. I mean, just look at, I just selected all the leases, right? Look at the right here, how much stuff is being affected by leases. And again, a lease changes the system, and that's why you see a revision number being bumped up. So let's get rid of all this junk for now. Drop this. And then we have all these registry endpoints, coordination. Let's get rid of this kind of stuff. Oh, more releases. See. Okay, so here we see there's a compaction that has been run. And then this looks more like a Kubernetes. We have pods, we have replica sets, daemon sets, right? So this looks more like the database, and there's actually not much in there anymore. Well, still a bit, but how many lines do we have? Oh, okay. So we went from 13,000 to 300. So almost probably 99% was just junk in terms of leases and updates to the system. That's why compaction, right? And we haven't even seen events in the system here in terms of event recorders from the controllers. So Kubernetes models its hierarchy as a registry. So they use a registry prefix in etcd. And if you look at the code base in Kubernetes, you also see registry a lot through the API server code base. And then they have the types, pods, config maps, deployments, services, secrets, blah, blah, blah. Then you will see the namespace that a secret is in, and then you see the actual secret. Let's take a pod, which is probably a little bit better to explain. Where's here, this guy. That's our local path provisioner that we just looked at. Okay. That means it's a pod. It's in the local path storage namespace. It's called local path provisioner or something. So Kubernetes knows it has this syntax of registry, type or kind, namespace, name. And that's how they can look up these things, these keys in etcd, because they all follow the same model: registry, kind, namespace, name. That's how the Kubernetes database or data model is represented in etcd. Now, obviously, there's also a value, right? This is just the key, the etcd, not the etcd key, the key for Kubernetes. The value is something like this, which doesn't really look nice, right? Why is it looking not straightforward? This is because for the core types in Kubernetes, they use protocol buffers to encode them for efficiency reasons. So it's basically binary in the system. It's marshaled into a byte array, this binary code. Now, if you use custom resources in Kubernetes, custom resource definitions and custom resources, because they don't use protocol buffers, they use JSON representation, you would actually see proper values here. Like you could literally read this because they are just JSON strings that you could read. But for the core types, like pods and secrets, it's protocol buffer encoded. But there is a nice tool called Augur. Where is it? That was written by Joe, I think. He's also like a Kubernetes expert and etcd maintainer. And it's a Go binary. And what it does, it just works for Kubernetes installations, but it has the protocol buffer definition. So it's able to unmarshal the keys and values, or the values actually. So I just did Augur extract and gave it the database, the Bolt database. So it reads the Bolt database. And now I see all the keys in there. Again, what we just saw, right? Registry, type, kind, namespace, name. But I can also ask it for our pod. What was it? Storage. Where's the pod? Service account. There must be a pod. Replica sets. We're getting close. Namespaces. Pods. Okay, this guy. That's our pod. And let's ask it for the representation. So I can do key and give it this key. And now it will unmarshal or read by a protocol buffer encoded value into nicely, like we can nicely read this. So let me pipe this into pod.etcd and now do a comparison of these two things. One that we did on the YAML, which is on the right, and one that we did on from etcd with Augur. And ignore these small ones here because they are just, the diff here is just because here's a nice string, like quoted string, and Augur doesn't do it. But you will find resource version missing. There's also a little bit of other stuff which is missing in the etcd representation, and that is because those are default values. But the resource version doesn't have a default value. So why is that missing? Well, I think you could give me the answer now, but I'm going to give it you in terms of time. Because we know what the resource version or the revision is for that object in etcd. We can literally just ask etcd for that. We don't need to store it in etcd because it's going to be redundant, it's going to be useless. So if we take this value of 559 here and we go jump back into our storage, storage. Where is it? Oh. We see there's a ref 559. Okay. So why should we store this value if it's already there from the data model perspective? And that is how Kubernetes, when it reads an object from etcd, it's not going to ask by default, it's not going to ask, hey, give me that resource version of that key, unless you tell it, but it will basically say, hey, give me that pod as of now. And then etcd will respond as part of the header, as the key value. It will tell you, oh, it has been created and modified at this point in time. So Kubernetes is taking this value, 559, and puts it into resource version in the API server. And then the API server does a nice YAML JSON representation, sends it to the client, and the client now sees, oh, resource version is 559. So without persisting this value, because it's already there indirectly in the database as part of the key anyways, we don't have to store it. So that is my question that I had in the beginning. If resource version is so important for optimistic concurrency control in Kubernetes, why is it not persisted? Well, in fact, it is. It's just not persisted as part of the value, as part of this value here, right? Here you won't see it because you already get it for free from etcd anyways when you read data, which is nice, right? And there's no like everything that you don't have to store, you actually save space, but you also know the source of truth will be etcd, and you just trust what etcd tells you. And if it's 559, you just take it, right? Which is nice. I think that's all I had. Let me just go back.
I have one more. This brought up a
Yep.
question for me because I haven't played with namespaces, and I use the default namespaces right now for the pods that I'm creating. Is that like okay and cool, or should people be creating?
Create your own namespace. Yeah.
And that's done inside that YAML for the deployment?
Well, no, you have to create it first. So if you have a deployment and you tell it, oh, deploy to build namespace, but the namespace doesn't exist, you get an error. So that's why you do kubectl create namespace build.
Okay.
And then you can do the stuff.
And then everything's stored better in the database because then it's under that namespace for your pod.
Yeah, it's also much cleaner if you want to do cleanups, right? If you want to say, I want to blow everything away for that app, you just blow away that namespace. But if you have everything in default, oh, what actually is it that I can blow up or like delete, right?
All right. I'll play with that today.
You bring up a very good point, Bill. Thanks. It's almost like I told you to ask these questions. So there's one thing that you might ask now, depending on your Kubernetes background. So I told you that Kubernetes uses these events from like watch events, right? From etcd to fill the local cache and everything else. And I also told you that if you crash and you come back up, you can tell the system, hey, given that resource version or revision, whatever, give me all the changes. And this goes back to our ListerWatch approach. Like, why is it not just a watch approach? Why is it a ListerWatch approach that we have here in Kubernetes? And what are some of the guarantees? Well, the controllers do the following when they come up. Instead of doing an immediate watch, what they do is they will do a list, which comes back to a range call, a get, basically with the prefix, and say, give me all the pods. And so let me show you that. What they basically do is they do etcd ctl get registry pods prefix. And that will give you everything under pods. Well, you can give it a namespace too. So, well, you basically give it this prefix, right? Oops. And then Kubernetes will go to etcd and construct a range call, and under covers it will retrieve those objects. And as part of the response, Kubernetes will also, or etcd will give you the resource version or the revision of the current version of the store. Meaning at that point in time, you get back 5 pods and the revision of the store is say 25. And then you can now see your screen. Oh, I don't know. Zoom just told me something. I hope you didn't miss me.
It's all
for
me.
Okay.
So all good.
You get all your pods, right? And you also get revision 25, meaning the store right now is at 25. Then what the Kubernetes controllers do is they will take the 25 and say, let's start a watch at 26. The next one, right? From the next change on, please tell me what's going to happen. And so if build starts creating new pods, you will get these new pods in there. So you have filled your cache with everything that is in the system, and you will get incremental updates to these objects as part of the watch, which is pretty nice. That's called ListerWatch, right? You list everything, and then etcd or Kubernetes will give you back the current store revision and all the objects. And then you take the revision and you say, oh, watch from this one, +1. That's nice. It just has, there's one There's just one issue with that, which is if you crash, and even if you persisted that revision somewhere, if you crash and you come back up, oh, well, let's say you crash and all the objects are going to be deleted. Someone deletes the whole namespace and you come back up and you say, give me all the pods. Kubernetes won't return you anything. You basically missed all the deletion events, which is, you can't even go back because there might be compaction, whatever, right? You could do some fancy tricks like I persisted my revision somewhere, but there's no guarantee that you will always see all these events, right? Again, remember, level triggered. So how do you prevent this corner case? Well, it might not even be a corner case, might be pretty normal, that you would be offline or crashed or for whatever reason, someone deletes the whole namespace and your pods are gone. But you would have to clean up maybe your database like a CMDB or whatever, right? You would actually have to do something with those deleted events, but you missed them because you were down during that time. The Kubernetes has a nice concept, which is a finalizer. And I think they took this from garbage collection or other runtimes, which have the same concept, which is you mark an object as deleted, but you don't really delete it right now because there are other actors which need to do something on it. And a finalizer is literally in an object, just a list. It's a string array in a string slice in Go that you say, hey, I'm build's controller, and if anyone is going to delete this thing here, I want to have the last call. And so as long as build's controller string is still in that object, even though you deleted that object and it's kind of marked as deletion Kubernetes, you can't update it anymore, you can't do any fancy changes, it's still there. And so what that means is if you crash and you come back up and you say, give me all the pods, you will actually see that pod. It's still there. It's just marked for deletion. And then in your code, the first thing that you would do is you check, oh, here's a new pod. Oh, that pod is actually marked for deletion. Oh, there's a finalizer in there. Oh, I'm the finalizer. Let me do something of my work. And once I'm done, you remove yourself from the list of finalizers. And if that slice is empty, like there's no more finalizers in there, Kubernetes will do garbage collect and then throw the object away. And then eventually it will be compacted and defragmented from the etcd database. So this is the only way how you can avoid missing events in Kubernetes, by having these finalizers. Because even if you have the watch, even if you have all the revisions and all the stuff, if you delete something, you won't be able to get it from Kubernetes. It's basically gone, unless you use the concept of a finalizer. And that is something that you might think it's advanced, but it's actually something that you have to learn very early in when you do these controllers in Kubernetes, when you write controllers or operators, because you might have to do cleanup work if something is deleted. If not, perfect. You don't need to do the finalizer stuff. Just ignore it, right? You don't care about this. But most often you need to do like deallocate an IP or do some billing. Like it's got deleted and you need to bill a time slice somewhere else, etc. That's where it is important.
I'm just naively thinking like, wouldn't it be enough to for a controller or any controller's object value, if it doesn't find any information about an object in the system any more than to assume that it's deleted or something like that, but it's kind of too risky.
It might work
unexplicit
I mean,
something.
If the logic allows for this, perfectly fine. The simpler, the better, right? Often, in terms of assumptions, often you have to make guarantees. Like you don't want to miss this kind of stuff. And that's where people start to bring in state into the controllers, right? They track these changes. They say, oh, actually this object was there, then I crashed. Now it's not there anymore. I do the diff. Well, it should be there. It's not there. What happened? But this gets tricky because now you deal with state in your local controllers, which you don't want. So typically the recommendation in Kubernetes is that all these controllers, they are stateless. They are only basically have the local cache from etcd API server, right? This watch stream. And then they fill their local cache. If you crash, you come back up. It's almost like in Kafka. You replay the log. You don't have state. But this then means you trust the source, which is in this case etcd or API server. And if the object is gone, you have to trust it. It's gone. But you don't know whether it was there before or not because you're basically stateless, right? You don't have memory from the past. And in your case, it might even be your controller crashed, another one took over because you have leader election. Now, how does the other one have the state and information? Well, you now have to replicate and consensus. Well, you're starting to solve problems which are already solved in the system. And that's what I like with the ListerWatcher and the finalizer approach. These are very nice patterns in Kubernetes that you can abstract and use in different systems as well to simplify your own logic, like level triggered, watch streams, change notifications, and these finalizer patterns to not miss events, right? Like in garbage collection, this primitive, and push all the heavy lifting to either an API server or etcd in this case. Yeah. I think this was a nice conclusion. I didn't meant to say this, but I just think that's maybe the gist out of this, right? We went pretty deep. There's a lot of things in the blog post that I didn't cover today, but maybe the gist out of this is that there are so many great patterns in etcd and Kubernetes. Like etcd is monotonic revision, right? You only ever append, you never overwrite. Meaning you have this linear history, and then Kubernetes, the level trigger pattern, the ListerWatch pattern, the revision optimistic concurrency, everything is based, again, on this revision. It's so fundamental, and that's why I said in the beginning, if you don't take anything of this meeting, but what a revision is, then it's the key in the bulk database, and it's only ever counting upwards, then you're good. And that's, again, it's very simple, and you build a very complex machinery on top of this, right, which solve all these distributed systems problems. And now you don't have to solve them in your logic anymore, which I like a lot.
And when you were helping me fix some bugs last week, you were looking at that number a little bit to look at change. I think I remember you asking about this number. Now I
yes,
know why it's important.
Yes, the revision is very important. I also looked in your case at the replicas and the instances, because the problem in Kubernetes is that you have these different actors, deployments, replicas, that's pods or components, right? And it's, oh, my deployment is there, I can see it, but I don't see the pod. Where is it? Well, then you need to go through the machinery and look at what did the deployment controller do? Oh, it actually did create a deployment. That's nice. And now there's an event created in the system, deployment created. And now the replica set controller kicks in and says, oh, there's a new deployment. I need to create a replica set for this. Well, creates a replica set. Or, well, in this case, actually, the replica set gets created by the deployment controller. The replica set controller gets this event. And now see, oh, there's a new replica set created, but I don't have the pods for this replica set. Let me create the pods for this replica set. And so once you understand these relationships between these layers and hierarchies in Kubernetes, it's easier to troubleshoot. What is still missing is kind of tracing, because these events and state changes that flow through the system, right now, there's no trace ID. There's a lot of work in Kubernetes which will give you a trace ID. So when you say create a deployment, it gets an ID, and then all the changes in the system will propagate that ID through. And then you can visualize this with something like Jaeger or Zipkin and see, oh, deployment, replica set, but no pods. Oh, well, something went wrong that line, because you have causality based on the trace ID, which right now, I don't think it's there. I think it's still work in progress. Great questions, everyone. So we're a little bit over time. I still have time, but this was basically the presentation that I had.
Yeah. Thanks a lot.
Thanks.
That was brilliant. I learned a lot.
Thank you very much.
Yeah, I really like the low-level insights and kind of taking apart things, so that I really like that approach as well. I keep recording for a bit, maybe for some questions, if that's okay for everyone, or should I turn the recording off? How you feel?
I'm good.
I have to head out anyway,
okay.
So.
Thanks, Bill, for joining.
Thanks for hosting this meetup. I really appreciate it.
Yeah, thanks for the support through GoBridge. We really appreciate that as well. And all the work that you do in general.
Exactly. And Bill, one final question. When is the book due? When is it coming out, the new book?
It's all done. I made some more revisions today, but I got
revision. There we have it.
I reached out to Scott Myers to get permission to use some of his images, and I misspelled his name, you noticed. So made another revision today. But July 1st, we're all set to start.
Nice.
July 1st. So yeah,
cool.
That's like 10 months in the making, man. Right.
So how long did you take for the other one, the Go in Action?
That was 18 months.
Yeah.
I really didn't. I was writing almost everything twice on the first book because I knew nothing back in 2015. Yeah. This one, it was more just tedious labor, more than anything else. So
nice.
Really, the book is about 8 years in the making when you think about it, but 10 years to write it all down.
Crazy.
I mean, 10 years, 10 months.
That's crazy.
I heard the quote, I hate writing, but I love to have written.
Yeah, yeah,
something
true.
like that.
I have like almost PTSD when it comes to writing books.
Yeah,
I
the
can write a
blank
blog
page.
post, and give me like 3 days. I'll write a blog post. I'm done in a week. But no, it's a lot of work, man. And then the revisions, and I did my own page setting on this one, which has been a total nightmare to figure out how to get a copy of something that can be printed in the same exact way.
Yeah.
It's a lot of work. Anybody who produces a book, I'm here to support and promote it because it's not easy.
No.
Yeah.
And honestly, I thought about writing about etcd and this kind of stuff, but I have the same issue. I'm more like I can do presentations, but writing is really hard for me. Even a blog post, it's just too hard mentally.
But I will tell you, if you're going to give these kinds of talks, writing the blog post first is really important because it allows you to figure out the language that you should be using. Because once you can technically write it, then you can speak it. So I think blog posts are critical for these types of things. I'm really happy you're writing blog posts with it. But eventually you get about 10 blog posts together. That could be a book. I mean,
true.
You have material for it at least.
Yeah, that's right. Again, thanks, Bill. Thanks for stopping by. And any more questions?
I just had like one question, like maybe in a kind of production setting, you won't have, because that's kind of such a critical piece, like everything is in there, like in, maybe in some kind of weird system, you could just look at an etcd database and kind of replicate whatever is going on, like just looking at these things or something like that. The question is like, you want to have like at least 3 etcd nodes so that they can go down or something like that. Is it like set up this way, like 3 nodes or like some odd number?
Yep. 3 is typical. Yeah,
typical.
3 is typical.
Okay. So, and then you have like some some kind of reliability guarantees that way. Okay.
Yeah, because you can't afford to lose the database.
It should never go down, and it's kind of like high. It's kind of not high volume. And you get a lot of just events, and so it's kind of constantly being used. And
Yep. And a lot of people also just say it's not like truly a database where you do a lot of writes because they are expensive when you go distributed with etcd because of all the coordination and the raft, consensus protocol, which has to go through, and then the replication and the latency there as well. And because it gives you these nice, strongly consistent guarantees, you can lose a node and then the whole system is basically has the same view. But at the other hand, every coordination is expensive in terms of latency. And if you lose quorum, the system is down, like cap theorem and all the issues gets in your way. Cool. So this was kind of my dry run for a couple of other talks that I also thought about giving here. Obviously, it was too long because usually talks are like 30 or 60 minutes, right? I just wanted to.
It's okay. Maybe I just for the record, I will just stop the recording so we have like the nice presentation, some questions. If you watch this up to this end, feel free to join Leipzig Gophers for interesting talks.
Yeah,
okay,
great.
Bye.